The last special type of transformations that we're going to look at and look at how to graph are absolute value functions. So we've already seen a simple absolute value function in transformations. That was just the absolute value of x, and you know what that graph looks like, and you could do all sorts of transformations starting with that parent graph and graphing it. What we're going to look at now is what happens if it was something else inside the absolute values, like a parabola, or a cubic, or a sine graph, or a log graph. What would that look like? How could we take the absolute value of any function? Well, you know that the absolute value, what it does is it takes negative values and makes them positive. So the only thing that's going to happen in this transformation is that all y values in f of x will either stay or become positive. So that's your transformation. We have to look at our original graph. We're going to graph our original function. And then we're going to look all our y values that are negative, we need to change them to be positive. And if we change them to be positive, what we're going to need to do is flip all of our negative values over the x-axis. That's what's going to happen. So we've already graphed y equals the absolute value of x. You know how to graph that. What's going to happen now is we're going to learn how to do this in a different way. So in y equals absolute value of f of x, the entire graph will be above the x-axis. I guess we can have y will be greater than or equal to 0. So let's look at an example and let's look at our steps for doing this. If I asked you to graph the absolute value of x squared minus 9, well, you could start with graphing the inside function. What does x squared minus 9 look like in our transformations? It's a parabola that's been moved 9 units down and looks like this. This blue graph is graphing the inside function first. To figure out what our absolute value graph is going to look like, all the absolute value does is it makes sure that all of your y values become positive. And so the entire portion of your graph that's below the x-axis, this part right here, that part is going to get reflected over the x-axis because you're going to take a nice point. Here we have a nice point like 0, negative 9. If you did the absolute value of that y-coordinate, where would it go? To 0, positive 9. So we're going to need to know where our x-intercepts are. In this case, they're at 3, 0, and negative 3, 0. Those points are still going to stay the same. But this part of our graph is going to get flipped up. The rest of our graph is already positive. It's not going to change.
So this would not have any effect as something like x squared plus 9 or x squared plus 1 because there's no x.
That's right. It only affects graphs where the y values are negative to begin with. Okay? And so the absolute value function will end up with all your y values being positive. Okay? As a part B, sometimes we've seen questions where I could have the absolute value of x squared minus 9, and then subtract 3 at the end of it. What would that do to our graph? It would move this graph here. I'll highlight it over top in blue. That's the graph of that absolute value. This minus 3 would move it 1, 2, 3 down. Okay? And I want to point this out because sometimes students, whenever they see absolute value, think, oh, it can only be positive forever and ever. But I have a minus 3 afterwards. Okay, that could move it down 3. And so this part, this absolute value, would be sort of this W-shaped looking graph. And then that minus 3 would move it 3 down. So that would be that blue graph. And you had the point 3, 3. So this point here would be 3, negative 3. Oh, I guess this is example 2, because I gave you one already. So if we know that f of x is a line, 2x plus 3, and we want to graph the absolute value of f of x, using our new technique would say graph 2x plus 3. That has a y-intercept of 3, a slope of 2, so down 2 over 1. It looks like this. What are the coordinates of the x-intercept? Something, comma, 0, right? Negative 1.5 or 3 halves. How could you find that algebraically?
You just isolate it.
You can put in my equation of f of x here, and this is the graph of f of x equals 2x plus 3. If I want to find an x-intercept, I could plug in 0 for y and solve for x. So I get negative 1.5. That's going to be important because when I go to graph y equals the absolute value of f of x, that point is going to stay the same, negative 3 halves, comma 0. This part of my graph, that's the part where my y values are negative. All of those y values are going to become positive. So for example, here I have the point negative 2, comma negative 1. Now I'm going to have the point negative 2, positive 1. In a sense, though, that green section is going to get reflected over the x-axis and now point up like this. The other part that I didn't highlight is already positive, so those points are going to stay the same. And this is going to be the graph of the absolute value of f of x, or absolute value of 2x plus 3. Does that look like our normal absolute value graph? Yes. And it is, in fact, something we could have done with transformations. So if you'd used your transformations unit to graph the absolute value of 2x plus 3, what does the 2 do? Does it affect your x or your y? Affects your x. Is it a stretch, compression, reflection, translation? It is a compression. You would multiply your x values by a half. The plus 3 might make you think 3 to the left. Why is it not 3 to the left? It ended up going negative 3 halves to the left. Because we'd have to, if we use transformations, we'd have to do this in factored form. So if you use transformations for this one, you'd have to factor out the 2, which would give you the 3 halves to the left. Multiply your x values by a half, then move things 3 halves to the left, and you would get this exact same graph. However, in this case, I think this new technique is easier. You graph the function inside first, and then whatever is below, you flip over the x-axis. So sometimes you get absolute value questions like this, where they give you the equations, you can graph the inside functions, and then just do the reflection. Sometimes they give you a graph, right? This one's graphed for us already. It's a chapter 1. We could have graphed this, right? Because you would know that your x-intercepts are at 0, -3, and at 2. And can you see that the equation is an x-cubed equation and a positive x-cubed equation? So from chapter 1 in polynomials, positive x-cubed equations act like lines with a positive slope. So we know the end behavior, it's going to be starting down here and ending up here. The multiplicity of each of those x-intercepts is 1, so your graph goes straight through each of them. So this would be your graph. We don't know how high it goes. This is why the graph is given. We wouldn't know how low that minimum is, but we're given this as the graph of f of x. So if I wanted to graph the absolute value of f of x on the same graph, again, I would say, well, which are the parts where my y values are negative? Well, my y values are negative here, and my y values are negative here. So if the absolute value makes those y values positive, that means that this section will get reflected up like this, and this section will get reflected up like this. What's going to happen to the other sections that aren't highlighted? They're staying the same because they're already positive. So the absolute value won't affect them. So I know that my final graph, that part will stay the same, and that part will stay the same. So all the absolute value does, and you might have run across a couple of these questions already in the review, all the absolute value does is take your negative y values and make them positive, and that results in reflecting those parts up over the x-axis.